Hi, thanks to the organizers for this invitation to a really fascinating conference. I'm really glad to be here. And today I'm going to talk about objects that are really, really low regularity spacetimes, basically zero regularity. But you'll see there's still something left from the procedure that we do. So this is the outline of my talk, and the idea is essentially to give you a broad overview of the subject. Towards the end, I'll be a little speculative about things I can do that might overlap with things that have been discussed here. So I'll begin with the motivation for causal sets, which comes from a theorem in Lorentzian geometry, which is what we call the Hawking-King-McCarthy-Malaman theorem, sometimes also added on Penrose-Kronheimer-Penrose. And then this brings me to the causal set paradigm, which is basically a discretization, a specific discretization of spacetime, in particular the causal structure Poset. And then I'll talk about the thing that I think is most relevant here, which is what we call causal set kinematics, which is a continuum approximation of the theory. And this has certain properties, because that approximation is very much in that causal set paradigm. And that approximation also implies local Lorenz invariance. It has a certain non-locality. Without violating causality, there's a non-locality to this discretization. And the fundamental conjecture, which is now again related to things that people have been talking about in this conference. I'll then spend the next part of my talk on geometric reconstruction, the question, I think I can call it synthetic geometry for causal sets. How do we extract information from this poset, this locally finite poset, geometric information about the spacetime that it's supposed to approximate? So I'll give you many, many examples of this. And then I'll end with something very speculative, so please shoot me down. These are ideas based on what we've heard in the last few days on the null distance function, ideas in Gromov-Hausdorff, and how we can apply it to causal sets. So here, to begin with, the Hawking-King-McCarthy-Malaman theorem states that if a chronological bijection exists between two future and past distinguishing spacetimes, then they're conformally isometric. So future and past distinguishability is, of course, weaker than strong causality, and that was the thing that Malaman did, was to generalize Hawking and the others' proof. And that's basically the idea that the causal structure contains, so the causal structure Poset contains everything but the conformal, so it contains all the information about the conformal class of the spacetime. So the only missing ingredient is the conformal factor. And so the original theorem had to do with chronological bijection, but when you're talking about future and past distinguishing, then this also means a causal bijection. And so the small little thing that we did was to look at whether we can just use the fact that it's not strongly causal, but it's future past distinguishing to also prove dimensionality. It is, in fact, there in the original Malaman proof, as we rediscovered recently. But one of the things that's interesting, and I hope I can talk to people about this later in this workshop, about how to recover topology when things are not strongly causal and you don't have Alexandrov intervals to help you construct the manifold topology. Okay, so what this tells you, and this is why it's a motivation, is that spacetime can be thought of as a conformal structure, the causal structure Poset plus this volume factor. And this is what inspires the causal set hypothesis, which says, well, let's just discretize this Poset. So this Poset, which is, of course, an infinite element Poset, we discretize it by imposing, again, an additional condition, which is that of local finiteness. We say the Poset also has to be locally finite, which means that between two events in the causal structure Poset, the Alexandrov interval fundamentally contains only a finite number of spacetime events. Everything else is mythical. And so we have this correspondence between order in the partially ordered set and the causal order. But we also have a very important correspondence between the cardinality of Alexandrov intervals in the Poset and the volume, the space-time volume. So obviously this means that there's some discreteness scale that we're talking about, and that will appear as we go along. And this was actually these ideas, I mean, they've been hinted at by many people over the years, that the causal structure Poset is kind of an important ingredient in quantization, and it was finally sort of put together by Bombelli, Lee, Meyer, and Sorkin. So here's the causal set paradigm, which is that forget about spacetime, the fine-grained structure of anything that you imagine to be spacetime is actually a causal set. So we think of all possible locally finite partially ordered sets, but it's not. That's not enough. We also need to tell you how, because we were inspired by the Hawking-King-McCarthy-Malaman theorem. We need to know how to make the continuum discrete correspondence. And this is going to be the main part of my talk. This is the emphasis that I want to put on it. And that's the continuum approximation, where you want this correspondence to happen. And so this is done by Poisson sprinkling. And so let me explain why we need something. The discretization process has to be done carefully. If I had regular lattices, so imagine in 2 dimensions, I have a light cone lattice, and I try to do a discretization, just a regular discretization, and I want to make a number to volume correspondence, right? I know immediately that I want that, first of all, I want that to be coordinate invariant. That should be a diffeomorphism invariant statement if I'm to get out spacetimes that I know and love, which are diffeomorphism invariant, right? So I can't do any kind of discretization, because if I did this regular discretization, I wouldn't be able to preserve a number to volume correspondence, because you can see under a boost, this very same volume that contains so many points is suddenly going to become empty. So there's no number to volume correspondence when you have a regular lattice. The only thing you can try to do, and this is inspired by ideas by T.D. Lee and others in the Riemannian context, is to do a random sampling. Okay, and that's done via a Poisson process, where you sprinkle, give me your favorite causal spacetime, and I do a Poisson sprinkling of that. And by that I mean with respect to the spacetime volume. So this is uniformly distributed with respect to the spacetime volume. And on average, so the correspondence works in the mean. On average, the number of points you have corresponds to the spacetime volume. But of course, there are fluctuations. Those fluctuations go like square root rho times v, where rho is the density of sprinkling, or rho to the -1 upon d is the scale of discreteness. And the question, of course, to mathematicians is this the optimal optimal distribution we have? I'm happy to work with it as a physicist, but these are questions that are open questions. There are some results Saravani and Aslambegi have on showing that it's almost optimal, but this is an open question. So we would say that a causal set is, so give me a spacetime, I extract from this random Poisson process entire ensemble, okay, of causal sets. And it's that ensemble and the properties of the ensemble that are supposed to encode the continuum properties, okay? And likewise, I can ask, well, when is a causal set? If you give me a causal set, does this look like spacetime? I have to make sure that it comes from a faithful embedding. Am I able to embed it into a spacetime where the ordering in the causal set corresponds to the ordering, the causality ordering in the spacetime, but also that on an average, the number of points you have in any given region. So in particular, you have the number of points is a random variable, and you have to have the fact that it's distributed according to a Poisson process. Okay? So also that because it's a Poisson process, there's statistical independence of different regions and so on. Okay, so this is kind of the bread and butter of my talk. Please ask questions. So one of the important things that comes out of this is, unexpectedly, is that you can recover local Lorenz invariance. And here, let's just look at Minkowski spacetime. Don't worry about the more general case. And the reason for that is rather subtle. All we have is a Poisson distribution. And if you look at the space of all Poisson sprinklings, then you can put a probability measure on that space, some mu. And because of the nature, because I said it's uniform with respect to the space-time volume, mu is also volume preserving, okay? And because of that, it's also Lorenz invariant, which means that lambda here corresponds to your boost, your Lorenz group. And if you look at the set of all, so suppose you wanted to pick a direction in your in this causal set, then you can pick any direction along the unit hyperboloid, okay, right? And so you have this unit hyperboloid. And a good direction map, however, would be one which is equivariant. So if I pick it in one sprinkling, then when I do a Lorenz boost, it's picked in the same thing. It goes over to a Lorenz version of that same vector. And so that equivariance is an important property. And so the theorem says there's no measurable map which is equivariant, because if such a map exists, so quick proof that basically you would induce a probability measure that's uniform on the entire hyperboloid. And that's non-compact, as opposed to the case in the Riemannian case where you have just a sphere, it's compact, you can do that, you can pick a direction on sprinkling into a Riemannian space. So this tells you essentially that you have Lorenz invariance. Okay. Another property then that comes out is the feature of non-locality. And here I will just introduce the idea of a nearest neighbor, which we call links, which sometimes I guess people also call covers, and also the notation for space-like related. So if I think of it precisely because of the fact that these hyperbolae can extend all the way up, and I don't want to lose Lorenz invariance, you think of this as an invariant hyperbola, not just of proper time, but also of proper volume, right? The space-time volume is the same between the intervals are the same. So if I was to look at a Alexandrov interval, then I could boost the second point here all along the hyperbola, and will get the same Alexandrov interval, which means that the probabilities which only care about that volume are going to be non-zero all the way up the hyperbola. So that means that I get nearest neighbors that go all the way up the hyperbola. Okay, this is the nature of causal set non-locality. And so, like I said, the probability for a link is given by, just from the Poisson distribution, by an exponential of minus rho of v, and links lie along the light cone, which means that these are graphs. It's very nice to think of them as graphs, but they're graphs without a fixed valency. In the worst case, in Minkowski space, they have infinite valency. So you can't just put currents along these graphs or do something cute with it. It's much, much harder to recover locality from this. Okay? So another feature of this is that let me just consider this causal set and say, well, can I construct the Cauchy kind of hypersurfaces for it? I can definitely construct space-like hypersurfaces, because all I have to do is look at a maximal set of unrelated elements, right? So things that are space-like to each other. That entire maximal set, so I fill it in as much as possible, is a good approximation of a space-like hypersurface. But does it capture all the information you need to develop, for example, a Cauchy problem? And it doesn't, because you have these funny links, which sometimes we call missing links, which is this guy here, which is not mediated by anything in the anti-chain. So this red set is the anti-chain, and there's a link here which is not mediated by that anti-chain. So the information that you have here cannot be enough. Somehow it's not a summary of the past, even though this causal set can be divided into the past of this and the future of this. So just to quickly say that, and this is another very important thing, is that since it's uniform, since this distribution is uniform with respect to the space-time volume, you know then that any set of measure 0 will not be realized, will almost surely not happen. in particular, it means that we do not have horismatic relations in the causal set, which is approximated by spacetime. And so it's an almost Lorentzian length space because we have the causality condition, but we don't, in any of these continuum approximation, we don't have the chronological or equivalent. You can say this is the chronological relation. It doesn't matter. And where now T is going, I'll describe this in the, yes. So that's a good question. I mean, I can talk to you about it maybe a bit more in detail later, but one of the ways in which we sort of try to get information about the spatial hypersurface is to thicken it. So we so I will describe this about, yeah. So, okay, so one of the things that you want to be able to do with this discretization is say that somehow there's a uniqueness, okay? But uniqueness up to scale, up to the discretization scale, which means that if I have a causal set and it comes or it's approximated by manifold 1, but also by manifold 2, then those two manifolds should be close to each other up to scale, discreteness scale, okay? And that's where you can see that a lot of the techniques that have been discussed here today are relevant. How do we talk about closeness of Lorentzian geometries by some kind of Gromov-Hausdorff conditions? And so there's a lot of work here on these questions. I'm still learning about some of them. And the question of whether, the most important thing is that we want to describe things that are row close, okay? Discreteness scale close. And that somehow has to come into the definitions of closeness. There's some recent work also that Ettore told me about, which I haven't had time to look at carefully, but I think there are these very interesting ideas of how you can get spacetimes from limits of causal sets. But the idea is essentially that all the physical information that you want is contained in that discreteness, and everything else is just your imagination. Up to that scale. So the main, okay, so I think I should hurry up, but I'll try to do my best to at least cover a part of this. So the idea then is, okay, let's say that you have this ensemble of causal sets. There's just order, there's number. How much geometry can you recover from this, right? There's no continuum, there's no regularity, nothing that we can appeal to, except the fact that we know it comes from the continuum. And that's really the key point. And it comes from the continuum in a specific way. So when we have labelings, so, the analog of diffeomorphisms are relabelings of the causal set, and nothing that is physical should care about the labels on the causal set. And so order invariants are label invariants. So things that, for example, if I were to count the number of nearest neighbors in this, it wouldn't matter how I labeled it. So that's an example of an order invariant. And so if we have a geometric topological observable corresponding to an order invariant, then we have a version of this fundamental conjecture, which I cannot pronounce, but which is in the field, which this is the country in which you can pronounce it, which is that if you have this kind of embedding into two different spacetimes, then at least with respect to that order invariant, those two, or that geometric invariant, those two spacetimes are the same, okay? So up to that scale. And so the question, of course, is how do we identify the right order invariance? And it's just been good guesswork. A lot of good guesswork over the years. And of course, that's where we start with, and then we try to derive it as much as possible from first principles. So that's our version of proof. But importantly, what we have is a Poisson process and the fact that you're sampling uniformly at random, randomly and uniformly. So I'm going to give you some examples. The first few examples were in fact already there in Miriam's CERN preprint, where he actually had many of these ideas. Apparently, when he tried to get, it never got published, because when he tried to get people to look at it, they said, this is a crazy idea. But many years later, it was actually codified. But this is the idea of a dimension estimator, where you're basically taking the fact that the number of elements on average looks like the volume. So let's take a flat causal diamond, is rho times that volume. And if you look at, calculate the number of relations you have in that causal diamond, you can do this calculation explicitly, you get an expression like this. And you can ask for, look at the ordering fraction. And you can see immediately that what you get is something that's this f of d is this dimension-dependent quantity on the right side. So the number of relations that you have over the number square of the number of the elements in that diamond actually is a dimension-dependent quantity. And so you can read off your dimension from this. So there's an actual dimension indicator that you have. We also have this thing called a midpoint scaling dimension, which is related to something that I think Olaf talked about, which is that if you have a Alexandrov interval and you divide it into two and you look at the volume in the causal set, of course, you look at the volume of the smaller diamond and maximize that volume, then the ratio gives you, again, something that is dimension dependent. And that's just from the fact that the volume in a Minkowski spacetime and the proper time are related in a very simple way. Another thing that you can do is to look at the time-like distance, which is, again, what one can use to give an almost Lorentzian length space, where you have a time-like distance coming just from maximizing the length of the longest chain of the chain. So you can construct a total order from x to x prime, many total orders. So a total order is just something which is, every point is ordered with respect to the other. And you look at the length of this, how many elements you have or how many links you have, and you just maximize. And that is a measure of the time-like distance. And in fact, this has been shown both by, I should actually have also included Brightwell and Bolobas, because it basically comes from some analysis that they did on random Posets. Okay, so one of the things that you might imagine with a causal set is that, okay, this is discrete. What kind of topology can it have? It can only have the discrete topology. How exciting can that be? And this is something we did many, many years ago, which is to ask, well, can you recover anything like topological information from a causal set? And the idea is the following, that here, I'll try to show it in pictures. You start off with that anti-chain, and then, so let's make it maximal in the sense you can't stuff in any more points which are space-like to A. And of course, by itself, it's just a set of points, there's no relations. The only topology you can put on it is the discrete topology. But once you start to borrow information from its neighborhood, from its future, then you begin to topologize the space. You begin to be able to put on sets on the space. And if you consider, so what we do is we look at a thickening of this anti-chain. So we go up to the future, all points whose past is at least up to some k value. So you thicken it up to the future. And you can do this in the continuum as well. And we did do this in the continuum. We showed that all of this construction works very well in the continuum as well. And that's one way of thinking of an evolution that is purely in terms of the space-time volume. And when you do that, and then you look at the past, you look at these sets that you form and the intersection of the sets, what you get, for example, is something like this. You can construct the nerve simplicial complex from this covering of the space. And from that, you can construct a homology. And so what we proved is that for large enough density and k, using the Durham-Weil theorem, you can show that the nerve simplicial complex that you extract from this is homological to the continuum spacetime spatial section, the homology of the spatial section. It's not homotopic. It's just falls shy of that, but it's actually homological. You can use the same idea of these volumes to define spatial distance function on it, basically by looking at the fact that in flat spacetime, there's a very nice relationship between the base size of the light cone and the volume of the light cone. So just use that, and then you get an approximate distance, and this is work, and you can also use it to extract dimension estimators. Okay, so another thing that's been very important is how do we get, so as you can see, I just want to emphasize here that what one is doing is one is looking at the averaging process. One is looking at the sampling process, where the space-time is there, but sort of as a ghost, if you like, and you're extracting information, but purely order theoretically. Okay? And so a very important development was the fact that one can construct the discrete Einstein-Hilbert action, which is called the Benincasa-Dauker-Glaser action. Glaser is, in fact, at the University of Vienna. They're a postdoc here, or research faculty here. And what you do is, the way you construct it is, so let me just say in a few words how you would imagine constructing this thing. You can construct a D'Alembert operator on the causal set, and you find that that D'Alembert operator, so if I look at this point here and I look at the past D'Alembert constructed from the past connections here, then it turns out that the only kinds of things that I need to look at are nearest neighbors from that point, next to nearest neighbors, and the next to nearest neighbors, and so on and so forth. I can basically layer my past in terms of nearest neighbors, next to nearest neighbors, and so on. And I have an entire layering of the past of an element here in terms of the size of the Alexandrov interval, but now this is the discrete Alexandrov interval. So the size of that Alexandrov interval is like looking at invariant hyperbole, and you basically corresponding to different space-time volumes. Okay? And so when you do that, this construction of the D'Alembert, when you put it now, go from flat space into a Riemann normal neighborhood and you do the calculation there, what pops out, because you know that in a Riemann normal neighborhood, if I were to calculate the Alexandrov volume of an Alexandrov interval, I get curvature terms, I get curvature corrections. So the idea is essentially take those curvature corrections, turn them around, and then use the volume to construct your construct the curvature. Okay? So it's just coming from pure geometric ideas. There's nothing mysterious about this. Yeah. Right. So the thing that happens is in a Riemann normal neighborhood, you kind of have, for a diamond, you have a direction. You have a directionality. So you get the R00. That's right. So that gives you a preferred time direction, and that gives you the R00 component, which you can also, quote unquote, extract out of this. But it's not really, so the important thing here is also because of the non-locality, we don't really have tangent space. I'm not sure if I emphasized that earlier, but that's another. So you can extract it. I mean, there are ways in which we've sort of just inverted it and got this expression out. Because this is one way of doing it. You can also count chains. Yeah. No, not because just the R00 component. Because you can get the Ricci scalar, but not the tensor. I don't think we have a way of getting out the tensor. I mean, it would be very interesting. These are sort of the open questions. We don't really know how to get enough information about the tangent space. So, yeah. So what you do then is, so what's really lovely about this action is that it just corresponds to counting in the spacetime region that you give me, count the number of links, then count the number of pairs of next to nearest neighbors, then count the next pair. So all you're doing is counting Alexandrov intervals, putting it together in this particular combination, which is kind of mysterious, but it still works. And you get out the Einstein-Hilbert action plus possible boundary terms. These boundary terms, for example, in Minkowski spacetime, give you, when you calculate that in the limit of the infinite density, you get out the boundary of the Alexandrov interval, the spatial boundary, the sphere. And there's a version of this recent version of this in curved spacetime. You can also get out the Gibbons-Hawking-York boundary term for spatial sigma. And here's sort of illustration. So if you have something with a maximal spatial hypersurface, then you look at the causal set, the maximal elements, the future-most elements of that. That forms an anti-chain here. And from that, you can again, in a specific way, construct the Gibbons-Hawking-York term. Okay, so I'm doing well for time. So there are many other examples in the literature. I just want to say that there's ways in which you can use chains. You can construct homology using chain complexes because you have totally ordered sets, and you can construct it using that. But the most important thing I want to say here is that uniformly sampled discreteness contains a lot of information. And that's because of the sampling, it's sort of the space-time is there, but at the end of the day, what you get is an order invariant. And you can go do your quantum theory with those order invariants as sort of observables of your theory. But just as a warning, typical partially ordered sets do not look anything like spacetime. And so there's a word of caution that we don't want to get spacetime out of all possible discrete, locally finite discrete orders. In fact, was a very old result due to Kleitman and Rothschild when enumerating Posets that states that the sample space of all n-element causal sets or locally finite Posets goes like this. It grows super exponentially. But the typical causal set here, this is in fact also the growth of the typical causal set, which looks like this. It has n minus 2 elements in the middle, n upon 2 in the middle, n upon 4 on either side, to the past and the future, and there's a huge amount of connectivity. And this is what dominates hugely the space of causal sets. And in the onset of the asymptotic regime, you can do this using numerical techniques, and you find that it's actually quite small. N is quite small before these things start to dominate. So the question you can ask is, well, should I be looking at space-time? Should I be trying to put space-time concepts onto such objects? Because these are typical. And there's more of a cautionary statement that this is not continuum-like in the sense that if I try to construct a Myrheim-Meyer dimension, I get something that's not an integer. If I try to look at the length of the longest chain, even as n increases, this thing just gets fatter and fatter. It looks like 3 moments of time in a space-time. It's really not what you want space-time to be. And if you look at, there's another indicator which I didn't talk about, but which is that if you looked at, just counted the number of Alexandrov intervals of different sizes and you looked at the distribution, then that distribution is also characteristic of the space-time, whether you're in what dimension of space-time you're in. And the distribution of these intervals in these KR-type Posets is very, very different from that of the continuum. So these are really not things that you want to be dealing with. So even if you're talking about causal sets, these are not the causal sets that should have meaningful space-time properties, at least within the causal set approach to quantum gravity. What's worse is that if you got rid of those, you have an entire hierarchy of these very layered posets, and hopefully you'll understand why these layered posets are also not like spacetime. So most causal sets, if you pick them out, will look nothing like a spacetime, okay? And so we don't necessarily want these objects to have a nice geometric interpretation of, except that they have, of course, definitions of protocausality. They have sort of a broad sense of what, causality. There's a definition of, you can put all those order invariants that we had, we can calculate them here as well. They're just not going to give you things that look like the continuum. So this is the dominant hierarchy. So while order invariants are defined for all causal sets, they only can carry geometric significance for continuum-like causal sets. I think I've rushed through my talk quite a bit, but in the last few minutes, I'll say the part that I was hoping to really rush through, but hopefully I will have some comments on this. That is that, you see, so one of the things that we want to understand is when are things close? Because if you gave me a causal set, so in quantum dynamics of causal sets, I would generate an ensemble of causal sets, a quantum ensemble of causal sets. I would be able to then extract an expectation value of these observables. I would like to say whether that observable corresponds to something that's continuum-like or not. But of course, because I have this discreteness scale that I have to associate with it, I want to know how close whatever I get is to the continuum. So the idea then was to, okay, so we're interested in things like the Gromov-Hausdorff distance. So how do we imagine this null distance function on causal sets? So one thing to do is to just take an antichain, one of these maximal antichains, because you need a time function. So what is a natural time function to use? And there are many ways in which you can try to construct that time function. You could strip off, so if you had, maybe I'll just use a blackboard here. I have the energy to do this. If you had, had a causal set like this, and I had, all the points here, then I could just strip off the minimal elements, and then I would get another set of minimal elements, and so on and so forth. And I could construct a time this way, a time function this way, so that would give me a foliation. Or I could use the volume the pass volume to decide on the foliation. So there are many ways in which I can construct a time function. But now the question is whether this null distance function is well defined. In general, if I didn't use if I wanted to just construct it without because of the fact that I have things that go all the way up here, links that go all the way up, I would get a very meaningless. Distance function if this would be as close as any point along the hyperbola. So I do need the time function to make sense of this, which is of course consistent. And the question you want to ask, so you can construct a null distance function, but the question is, how do you obtain a Gromov-Hausdorff distance function for this? So here's sort of preliminary work that we're trying to do using this class of 2D orders. I think Olaf mentioned it, the idea of intersecting two total orders. These are called 2D orders, and they actually are good ways to describe two-dimensional spacetime. So we just looked at a very simple class of orders. We're looking at, I should say, this is work in progress with my master's student. And so you have a ground set, and then you have a set U1 to UN, which takes values in this ground set, but it's not repeated. And so similarly with V, and you construct the 2D order by the intersection, where you say two elements are related to each other if both U as well as V values are smaller than, so if they're both ordered in this way. So you can look at, of course, you can construct from these 2D orders the totally ordered set, where you pick all of them to be in this way. So you can get out a chain. You can also get out an anti-chain. So those are two examples of a 2D order. And of course, you also have the randomly sampled order, which turns out for this class of 2D orders is actually the most dominant one. And that's, of course, the one that's most interesting to us because that looks like space-time. But we also know that 2D orders are special. We can embed them into the light-like lattice. Okay, there's an embedding that you can do, but you have to be careful because the U and V values, they can't lie on each other's light cones at all. Okay, the points can't lie on light cones. So you can't use the same U or the same V value. So on the light cone lattice, however, you can define a very nice null distance function, right? I mean, the null distance is very well defined, just in terms of the U and V coordinates. And what you want to do, so you want to construct the Hausdorff distance between two subsets of the light cone lattice. But then, given these 2D orders, you also like to look at the embeddings then into the light cone lattice and take the shortest Gromov-Hausdorff, shortest Hausdorff distance between those embeddings to get the Gromov-Hausdorff. But the way in which you get the distance is through the null. So that's the exercise, because this is what physicists like to do. We are not happy with existence theorems. We'd like to see how much we can calculate from it. And so these are sort of very preliminary results. I wouldn't even call them results, at least the red ones are not. They're things that we're playing around with and just sort of getting values for these. So let me just summarize it. So if you looked, for example, at a chain, an anti-chain, and one that's a little bit bigger, then you have, of course, just the distance of 1. Similarly for the chain and a chain that's just one bit bigger. So you can see that it's doing the right thing there. But also the chain, the anti-chain and the chain, right? The totally ordered set and the totally unordered set. These have a distance which is dependent on n. So if you can see this, you can calculate that distance and it's equal to m, where n is either equal to 2m or 2m plus 1. Okay, so this is an exercise in getting the right distance for these. You can also, so one of the things that, so we would of course like to go over to the random Poset, but we're still struggling with that. But what we asked is, let's look at the layered Posets. Okay, the layered Posets we had, or that I showed you a little while earlier, and ask how, can we calculate the distance for these? And definitely for the bilayer Poset, which is sort of second in the hierarchy, which comes after the 3-layer Poset, the bilayer Posets, we can see that approximately for large n at least, the distance between the chain and the anti-chain are equal. So you can basically start making up a map, of distances between these special Posets. And for the KR Poset, we're not fully agreed on these numbers, so that's why they're in red, so please don't take them very seriously. But essentially, it looks at least that so although the distance between the anti-chains, so as you layer things, they look more and more like a chain, and that's working out to be the case. It looks like it's working out to be the case, and it's therefore further and further away from the anti-chain. So these are good things for us. These are good constructive ways in which we can then say that, okay, this distance is doing what we wanted to do for the 2D orders. And here's a conjecture, which I really don't know whether it's going to work out, but this is what we would like to see, is that for any epsilon greater than 0, we want to see that there exists an n such that any two different realization of the random orders, which is the continuum-like orders, are such that the distance between any two realizations is less than or equal to epsilon. This would tell you that this distance function captures the idea that you have things that are really geometrically close, but that's where we're at right now. So thank you very much for your attention.